Welcome back, everybody. The topic this week, since we are going to look at different types of algorithms, is to remind ourselves quickly about what we did before the Easter break, where we discussed Fourier transforms and also discrete Fourier transforms. We started to scratch the surface of that. The discrete Fourier transforms are actually mathematically a very interesting tool. And as you will see, they link well with an algorithm which is called the fast Fourier transform, which was ranked as one of the top 10 algorithms in the 20th century. And if you're doing signal processing, a fast Fourier transform is an essential algorithm. We are not going to discuss that. You will find links to it in the lecture notes. There are books on fast Fourier transforms. One typical application, and you will see that a little bit later, without us going into the details, is when you're dealing with polynomial multiplications. So you can have a considerable speed up if you rewrite that in terms of fast Fourier transforms. And what you will also see is that this Fourier transform, the discrete one, reminds us a lot about a polynomial approximation to a given function. So there are many nice things which belong more to the field of Fourier transforms, which we will not look at. But the quantum Fourier transform, with its basic mathematical expressions, is something which is very important in quantum computing. The original algorithm for finding eigenvalues of a many-body problem was done with the phase estimation algorithm, which is based on a quantum Fourier transform. So we will discuss that next week. Today, we are going to go through the basic mathematics of Fourier transforms and the quantum Fourier transforms. And if we get time, we will start looking at the circuit for setting up a quantum Fourier transform. Now, the quantum Fourier transform enters also Shor's famous algorithm for factorizing integers. And that is an algorithm which really made the field of quantum computing explode, because suddenly people were afraid that the standard factorizing algorithms, which is using when you encrypt data, could be a danger. So we discussed also before the break possible paths for project 2. And one of these could actually be to study the quantum Fourier transforms and look at the phase estimation algorithm as a way to calculate the energies of a quantum mechanical system and compare that with what you did with the VQE. So one of the reasons why this algorithm, the phase estimation algorithm, is not used is that the circuits tend to become very long. And the VQE approximation, which we have been using, which is a mix between a classical optimization part and the quantum mechanical implementation of specific gates, is an algorithm which is much more efficient. So, however, we could have a variant of project 2 where we look at quantum Fourier transforms, and people can elaborate on that, and look at the phase transformation algorithm or Simon's algorithm. We have Shor's algorithm, which is also a possibility. And then I know that some of you wanted to extend project number 1 to look at more generalized way to attack a quantum mechanical problem like the Lipkin model with more than just 2 or few qubits. That's another possibility. I'm also going to make one variant which deals with quantum machine learning. That part will be more a self-study part because we're going to have a common theme during the lectures. So there's always a problem when we have this kind of self-study courses that we cannot cover everything. However, I hope that after we've gone through the quantum Fourier transforms and some of these algorithms, that we can have some time towards the end of the semester to discuss quantum machine learning as well. That's, after all, in the name of the course. So this is at least where I am when it comes to projects. And the plan is to have them ready for towards the end of the week. So you can start looking at the next step. Now, a brief reminder on Fourier transforms. So I'm going to quickly go through the slides which we had from before the Easter break, and quickly remind you a little bit about Fourier transforms. And what we focused mainly on before the break was actually the continuous Fourier transform. And we didn't say so much about the discrete Fourier transform, which is the one which we are going to deal with today. So if we then go down a little bit, so one of the important aspects which led Fourier to propose an expansion in terms of sine and cosines is the fact that we have periodic functions, so the function which repeats itself after a certain period tau. And that's a very important aspect, and we encounter that in many, many applications in science. So Fourier transformations and the whole machinery around Fourier transformations is something which it's impossible for you not to have heard about it or seen it. It's such an important tool in the analysis of data that it's impossible not to deal with it or have seen it. So we went through some simple examples. The basic approximation is that there is a function f of t, a periodic one, which we could rewrite like that. You would normally rewrite this in terms of sines and cosines. So essentially what you have here is what we went through on the whiteboard before Easter break. And then we can rewrite this Fourier transformation in terms of exponentials. And sometimes you can also see this in terms of just the real part. And the coefficients are complex numbers, and except for the C0, which is a real number. And you can encounter this in terms of just the real parts of the exponentials, or as it's written here. That's a typical form which you find. And then we went through the determination of these, and we're using the orthogonality of the functions. And then we found that these coefficients, C, are then determined by the function which we have, and then multiplied with this quantity. And these exponentials, which you see here with the arguments, they're normally called the harmonics. And a pretty common way to label these coefficients is just to use this one, and you normally call this a Fourier transform. And if you multiply the right-hand side, the left-hand side with e to the plus 2 pi I kt and integrate, then you get the inverse Fourier transform. And things which we showed was the independence of the interval length. We discussed that. We also discussed the change of period. These are technicalities which we looked at. And typical periods, which are often used, is a period t, which can be minus 1/2 to plus 1/2. These are typical periods which you encounter. And sometimes you change t here with or s with x, and then you refer this to the length sometimes, and then you will typically see a period which goes from minus L, the length of an object, divided by 2 to plus L, or you can start at 0 and go to L, just to give you examples of periods which you may encounter. And we looked at an example with a square well signal, and looked at how many terms we needed. And in this specific case, we would actually, in order to get it right, we would need an infinity of terms, but we get a decent approximation with something like a 500 to 1,000 terms already. And these were things which we looked at last time. And then towards the end of the lecture last time, we discussed the discrete Fourier transform. And this is where we're going to start today. And then look at the discrete Fourier transform and how we are going to encode that one in a quantum way. But let's take a look at the classical discrete Fourier transform first, so that you guys can gain some kind of mathematical insight about the Fourier transform itself. And then you will see that what comes afterwards are more technicalities. And there are technicalities about the way we encode the information when we are dealing with a quantum Fourier transform. And then next week, we will start looking at how we actually set up circuits and how we can define them and then run calculations with them. And this could be part of a project number 2 here. So let's go back then to the material for this week. This was just a quick repetition. So this discrete Fourier transforms, as you can see, is a kind of tool. If you have studied signal processing, this is just an essential tool. You can't avoid it. And you will find it in applications like speech recognition, data processing, optics, acoustics. Actually, there are smart ways of writing the filters in a convolutional neural networks in terms of Fourier expansions. And these are normally called Fourier filters. And they're given often a better approximation to the filtering in convolutional neural networks. So one of the famous algorithms is actually this fast Fourier transform, and that uses a special relationship amongst the roots of unity to compute the entire DFT in typically n log n, where n is the number of terms you have. As we will see here a little bit later, you can actually use this DFT to find a polynomial expansion of a given object. So if you're dealing with polynomial multiplications, and if you just think of the smart way of doing that, Horner's rule, you may have heard of that one, to do polynomial multiplication. If you have 2 polynomials of different degrees, this can be done much faster with a fast Fourier transform. So we are not going to touch that, but there are tons of books on these, and there's one book which you can download for free from Springer, which is Fast Fourier Transforms, Algorithms and Applications, and I also put it under the GitHub address, if you wish to study fast Fourier transforms by themselves. So as I said, this is something which has been ranked as one of the top 10 algorithms in the 20th century. So other algorithms are like the Metropolis algorithm. You have algorithms like Householder's algorithm for tri-diagonalizing a general matrix and then preparing it for diagonalization. And you have 7 other algorithms which are ranked among the top 10, really top 10 algorithms used all over in mathematical sciences and computational science. So the Fourier transform is an essential element. But we are not going to look at fast Fourier transforms. So let's go back to where we were last time and look at the discrete Fourier transform and use that as a way to prepare towards the quantum Fourier transform. So as I mentioned to some of you before we started today, this is a topic which I've never liked that much because there are tons of indices and it's easy to get lost. So let me just bring up the whiteboard and let us set up the expressions for a Fourier transform. So I'm going to use X and Y here, and later I'm going to change indices as well. So I hope it doesn't make too much confusion here. But what we typically have when we look at the DFT, so this is a discrete Fourier transform. So this is meant as a kind of prelude to the full quantum Fourier transform. And I'm going to use the acronym DFT, not density functional theory, but discrete Fourier transform. And we would typically have a vector X. And if we use this ket notation, which is actually the same as this notation here, we would have a given number of components, x0, x1, and xn minus 1. So in our case, this could be a vector which represents a given qubit state. We could have something like 10 qubits, and then we could make an initial state based on these 10 qubits, which would then be the tensor products of the different 10 qubit states. Then the discrete Fourier transform is something which outputs a vector. So each entry of the output vector, so let's write that one, each entry of the output after the DFT, so this follows very much the continuous case. So instead of these functions which we had f tilde of k, we would now have a discrete sum here of n. So there's not a continuous sum, an integral, sorry. And then we have x of j, where the xj's are the different components. And then we have e of 2 pi of I. And then we have j times k divided by n. So now I'm just singling out j and k because these are the indices or the subscripts of y and x. But later I'm not going to put in parentheses here because else I'm going to go crazy with all indices. Okay, so that means that the vector y, if we then move on, this vector y is simply going to be given by 1 over n. And then we have the different components here, where we have a sum over j from n minus 1. And then we have xj e to the 2 pi I of j. And this is multiplied with 0 divided by n. Because we have the first component, so this component which you see here, this component is nothing but y0. So let's just put that in parentheses. And then obviously the next one will have a number 1 instead of 0. That is going to be an xj of e of 2 pi of I multiplied with j multiplied with 1 divided by n. And then this just goes down all the way to the final term of xj of e of 2 pi of I of j. And then I have n minus 1 divided by n. And that's the last term. So these xj's, they can be complex numbers, general complex numbers, general complex. And what we have is that j runs from 0, 1, up to n minus 1. And the y of k, also complex numbers, are also complex in general. And k runs over the same integers as j. So if you now look at a specific example, and we discussed that briefly before we ended, before the Easter break. So if we now take a simple example here, we can now look at the case where this x vector is given by two elements, 1 and 2. So this is our vector. And in this case, we have x0 is equal to 1 and x1 is equal to 2 here. If I then look at the y values, so I would then have y0, which is simply 1 over square root of 2 plus, and then I have 1 over square root of 2 multiplied by 2. And that's obviously 3/2, 3 over square root of 2. And similarly, I have for k equal to 1, I get the next term, which is y1, which is then simply 1 divided by square root of 2 plus 2 divided by square root of 2. And then I have e of I pi, which is minus 1. So when I bring everything together, this gives me 1 over minus 1 over square root of 2. So what it means is that I have found a transformation here where I have y, which is now given by a matrix U multiplied by the original vector x. And if we look a little bit carefully at what we have, so this is the same as the matrix U multiplied with a vector of length 2, which has the components 1 and 2. So when we look a little bit more careful at this, what we will see is that this matrix, when we do the operation on only a vector with 2 elements, this is simply given by 1, and then we have 1, 1, and minus 1. Now, there's no quantum mechanics here, but we do actually recognize this quantity as a famous matrix in quantum computing. Does anyone remembers the name of that? Yeah, that's the Hadamard gate. But keep in mind now that, and actually you're going to see this one again and again. So when we operate with only 1 qubit, what you will see then is that this Fourier transformation can be represented by a Hadamard gate. If we're dealing with 2 qubits, we will have a Hadamard gate, and then we will have rotation gates, as you will see just in some few moments here. So the Hadamard gate is something which we will encounter again when we look at the quantum mechanical case. So this is a very special case because we have a vector of length 2 only. And you will see the same thing when we go quantum mechanically. We will also get a transformation which looks like a Hadamard gate. Now, in this case, these are just classical operations. And one of the things, just quickly, let me quickly remind you of that. If I take this matrix U of T of U, the transpose of that one, we know that this one is actually equal to 1, 0, 0, 1. So this represents an orthogonal transformation. Actually, the transformations which we are dealing with, they represent unitary transformations when we deal with the discrete Fourier transform. So it means that the DFTs, or these discrete Fourier transforms, they represent vectors, and these vectors are orthonormal to each other. And I just wanted to show you this kind of minor technicality here before we move on. However, before we look into that one, I wanted to remind you of something which you may have seen before. If not, let's just take a look at a specific case here. So if you now look at this type of transformation which we are going to make, this type of transformation which you see here, so this is represented by a matrix U, let's do a small digression first. So a small digression. And that small digression, even if we are not going to discuss it, actually leads to an important application of Fourier transforms, which is the fast Fourier transform, or for instance, polynomial multiplications. So if you now look at a polynomial expansion, so a polynomial expansion of a function means that we have a function f for some value x of I, and this is approximated with a polynomial of a given degree. So a polynomial of degree n minus 1 of x of I, and I'm going to skip this subscript. I'm just going to write it as a px of I. And we know that this one is given by a sum from j equals 0 up to n minus 1, and then I have an aj x of I to the power of j. So which means again that we have a0 xi 0 plus a1 xi to the power of 1 plus to the final an minus 1 of xi n minus 1. Then we can write a vector p of x which contains all the values. So we are going to write a vector p like this, which is now a vector which contains p of x0, p of x1, etc. down to p of xn minus 1. Now, this is probably something which you have seen written in terms of a famous matrix in linear algebra. Does anyone remember what that matrix? You can actually rewrite this as a matrix, and I'm going to call this matrix for V, because that refers to the first name or the first letter and the last name of the person who came up with this, times a vector A, where this vector A contains all the coefficients here. Has anyone heard of this kind of matrix? It is a famous matrix in the polynomial approximations and in linear algebra. And it has actually an analytical expression for the inverse. Yes, this is the Van der Monde matrix. So let's just go over to the definition of it. And this matrix V is now given by 1, 1, all the way down here. These are all ones. And then we have x0 to the power of 1, x0 to the power of 2, and then x0 to the power of n minus 1. And then I have x1 to the power of 1, x1 to the power of 2, x1 to the power of n minus 1. And this goes all the way down here to xn minus 1 to the power of n minus 1. And here I have xn minus 1 to the power of 1. So this is called a Van der Monde matrix. This matrix is actually interesting because it has an analytical expression for the inverse of the matrix. And it's widely used in this kind of approximation theory. So this would be the case where you have, let's say you have 10 points, and then you use all 10 points to fit a polynomial of degree 9. You know, if you have 2 points, you can fit a straight line. If you have 3 points, you have a square function. If you have 4 points, you can fit a cubic function, etc., etc. So this means that you use all the information which you have to make a fit of a given function in terms of a polynomial. And if we now look at the Fourier transform, so this is similar to the Fourier transform. So what I'm going to define now is just a quantity W, which is given by the exponential of 2 pi of I divided by n. If I then look at the Fourier transform which I have, these are some of the entries which you now will see. So if you now look at this pattern which you have here, with x0 to the power of 1, x0 to the power of 2, etc. If you now look at some of the quantities which we have, so if I take x0 equal to 1, and I look at the Fourier transform, this will be the same as 2 pi I multiplied with 0, multiplied with 1 divided by n. And that is simply 1. Then I can do the same thing with the x0 squared for the Fourier transform, because the basic equation which we have in the Fourier transform is defined by this quantity omega here. So if you go back to the Fourier transform and you think of this polynomial approximation which you have here, this term here, that one, and you look at what we had for the discrete Fourier transform, this term here. So you see that there is an xj here, but then we have this 2 pi I to the power of j. And this 2 pi I to the power of j is the same thing which we encounter in here. And then the aj is just going to be a coefficient, this xj coefficient, which we have here. So if we look a little bit closer at these kind of small manipulations we have, this will be the same as E. And then I have 2 instead of 1 times 2 pi of I divided by n. And this is also equal to 1 because we have 4 pi. So this will always be a series of ones here. And if I then look at the next type of terms which I have, if I take x1 of 1, This is e to the 2 pi of I divided by n, and this is the same as w. If I take x1 squared in the same way as I'm setting up this van der Monde matrix, this is the same as 2 times 2 pi of I divided by n, and this is the same as omega squared. And then you will see that x1 cubed is the same as w omega squared cubed, sorry. And then it goes all the way up to x1 to the power n minus 1, which is the same as omega of n minus 1. You can repeat the same exercise now and just take a random number here, x2 squared, which is the same as e times 2 pi times 2 actually of I divided by n. This is the same as omega q to the power of 4. That means that the matrix which we have, the matrix U which we wrote, can be written as a general matrix, which looks like this. So we have ones here, and then we have ones along here. But then we have omega, and then we get omega squared, omega cubed, all the way up to omega of n minus 1. We have omega cubed here. We have omega to the power of 4, etc. And this goes all the way down to omega of n minus 1. And finally, if we just continue here, we end up with omega of 2 times n minus 1 here. So that will be the final one. So these are the matrix elements which we have. Sorry, this should not be, this should actually be that one squared. Omega of n minus 1 squared. So if you look back at what we had in the previous case with this van der Monde matrix, the values for which we have the function are here just given by x to the power of n minus 1. So this quantity here corresponds to the same quantity which we have here. And we have defined this omega in terms of this quantity here, which enters a discrete Fourier transform. So you can actually view a discrete Fourier transform as a polynomial approximation. And this fits extremely well if you have periodic functions. Now, this trick with the Fourier transform, the way you can interpret it in terms of a polynomial expansion, is what has been used in a fast Fourier transform when you typically multiply two polynomials. And it was actually, the first paper was this written in, I think back in 65 from people working with signal processing. But it seems that Gauss did this back in 1805. So this is always one of these kind of intimidating things. Every time I've been looking at algorithms, Mr. Gauss has been putting his hands into one or the other of the algorithms. It's actually quite impressive when you think of what Gauss actually did. So he came up with the fast Fourier transform. He actually discovered this pattern back in 1805. That's quite amazing. In addition to everything else, Gaussian elimination, Gaussian quadrature, efficient ways to integrate, Gauss-Jacobi iterative schemes, yeah, almost everything. Gaussian probability distributions. It's the list is intimidatingly long. Now, it's amazing actually. So one of the things which you can do with this matrix is that this matrix actually has an inverse. So I'm just going to mention it for you. And the inverse of that matrix is has essentially the same elements as you would have with a van der Monde matrix. So this has ones along here, just ones, and ones, and ones. And then the matrix elements which you get are just the inverse of these ones. So this will be the same as W of n minus 1. So I'm not showing you how to get the inverse, but it's actually not that difficult. And this is of n minus 1, and this goes all the way up to w of minus n minus 1 squared. Then, when you look at a specific component of this, you can actually show that this is an orthogonal transformation, or unitary transformation in this case, because the omegas are complex. So what we have then, so the orthogonality, or in this case, unitarity, is something which is easy to demonstrate, because you can now just take one of the matrix elements. Suppose you take the element jk. This is now given by 1 over n, and then I'm going to have an L equals 0 up to n minus 1, and then I'm going to have an omega j to the power of L, and then I have an omega of minus L to the power of k. And this is something which is equal to 1 over n, and then I would have an L equals 0 to n minus 1, and then I have an omega of j minus k of L. And then you simply have to go back and look at the definition of omega, which is e to the 2 pi of I divided by n. And then you can see that this one is equal to 1. Only if j is equal to k. And that shows the orthogonality. There are other ways of doing that. And there is an alternative in the lecture notes, which I put up. So the coupling to this type of representation of polynomials, which I did here as a kind of digression, this is what forms the kind of basis for the fast Fourier transform. And if you go into mathematics texts, you will find a lot of mathematical theorems and proofs using fundamental theorems of linear algebra, of general algebra, etc., which then are used to prove the basis for the fast Fourier transforms, which we will not discuss, because what we want to discuss is actually the quantum Fourier transforms. So I will leave that discussion about the fast Fourier transforms as something of more special interest if you want to dive into the literature. But let's get to the interesting topic, which we need to discuss a little bit more. So these are the quantum Fourier transforms. And I'm just going to use the QFT as an acronym here for that. So what we are going to look at now is a specific transformation which deals with the qubits. So we are going to have a qubit basis. So this could be a qubit basis for just one qubit. It could be a qubit in state 0 and qubit 1. So we are going to deal with a computational basis as before. So we are going to look at a system now which has n qubits. So if I have n qubits, how many basis states? So the qubits take states 0 and 1. So how many states can I make with n qubits? 2 to the power of n. So I'm going to use another number here, so which is the total number. So we'll have 2n basis states. And I define that with an uppercase letter n, which is then 2 to the power of n. That's the number of basis states which I have. So the QFT, what that is, it's a linear operation that transforms orthonormal basis states to a new set of orthonormal basis states. So one thing you should keep in mind is that if I have an orthogonal transformation of a basis or unitary transformation, and if my basis is normalized and orthogonal or orthonormal, the unitary / orthogonal transformation preserves orthogonality and it preserves the norm. So keep that in mind. So if so let me just quickly remind you of that. So when I have a new basis, which we label as y, and I use this transformation u times x, then I have a transformation here. And since we are dealing with quantum mechanics, we're dealing with unitary operators. This is given by the identity matrix. And this transformation preserves orthogonality. And the norm. And it's pretty easy to see that because if you have two vectors, so let's just call them a vector xi and a vector xj, the orthogonality, and if it's normalized as well, has to be equal to a Kronecker delta. So that means that if I now look at the two new vectors, yi and yj, that is going to be equal to xi, and then I have the unified transform times u times x of j. And you see that immediately, since this is equal to the identity matrix, this is equal to x of I, x of j, and that's equal to delta ij. So this is just a quick proof that if you have an orthogonal or unitary transformation, then your norm has to be preserved. So the QFT is a linear transformation or linear operator, is a linear operator that transforms an orthonormal basis. It can be just orthogonal, but normally we always normalize it. An orthonormal basis into a new orthonormal basis. So the original basis which we have, so you could assume an original computational basis, an original computational basis, and this is where you're going to see how the transformation which we're going to make comes into play. So suppose now that you have an original basis, which we simply label as state 0. This doesn't need to be a 1-qubit system. This could be a system which has n, uppercase letter n, basis states. So we could then have 1, next state, 2, up to states, n minus 1. Okay? Now, just to prepare the ground a little bit for what is going to come in terms of a compact notation. And this is a kind of compact notation where I'm going to put you asleep here because it's perhaps not the most exciting thing, but it allows us to compactify everything. So you could think of 2 qubits. So suppose now that n is equal to 4, and that follows from n equal to 2 qubits. And what we will have then would be a state, which we label 0, 0, which is the same as the tensor product of the original basis state 0 and 0. We had 0, 1, which is the tensor product of this guy here. And we would write this out as 1, 0, 0, 0. This would be the same as 0, 1, 0, 0. And then we have the two other ones. This is 1, tensor product with 0. And finally 1, 1, which is 1 tensor product with 1. Okay. Now, what we can do now, if you go back to that basis which we have, so over n equal 4 bases, this is something which we now have labeled as 0, 1, 2, and 3. And we have then to assign a specific state to it. So what we will typically do then is to have this one to correspond to that. We do this one in terms of that. And we do this one in terms of state 2, and this one in terms of that. So this is going to lead to a more compact notation, which we will introduce after the break. But just keep in mind that what we are doing here is that we are making up a basis, an initial computational basis, which for the 2 qubits case is given by this state 0, 0, 0, 1, 1, 0, and 1, 1. And then, in order to compactify it, what we do then in a numerical representation is to have a pointer which now contains a vector 0, which points to 0, 0. Vector 1 points to that one. Vector 2 points to this, and vector 3 points to that. So later we are going to use a binary representation for these specific states. Okay, just keep this kind of picture in mind, because we are going to reuse that one to write the Fourier transform in a more compact way. I've gone a little bit over time. So what we're going to do now is to set up the equations for the quantum Fourier transforms, but we need to do some further manipulations. So before the break, I showed you what this basis can represent. Now, what you find here is what we would call a compact way of indicating what are the basic components of that specific state. And we are going now, afterwards, we are going to rewrite this in terms of a binary representation. And that's going to give us a more compact way of setting up the quantum Fourier transform. But let's take a look at the basic definition of it. So the quantum Fourier transform takes the same expression as what we had before. So we would have a state y, but now we divide with the number of basis states which we have. So it's not the lowercase n. And then we would have a sum from k equals 0 up to n minus 1. And this is given by e to the I of 2 pi. And this state here, we are going to, I should rewrite it more like a state. So let's just rewrite it like this. This is just a state j. So we have the subscript j here, and then we have k divided by n, and then we have the state k here. So if we take the 1 qubit case, just to show what that looks like, in order to get some feeling. So we would have then n equal 2 to the power of 1, which is equal to 2. And the states which we are used to then are the computational basis states, 0 and 1. So these are the type of computational basis states which we have been assuming that we can use for a given system. And then you would typically ramp this up when you have 2 qubits, 3 qubits, etc., etc. So if you then look at the transformation of the, let's say, the state 0. So we could now write 0 tilde here just to indicate that that's this new transformed state. So that would be 1 divided by square root of 2. And then I have the sum from k equal 0 up to 1. And then I have my e of 2 pi I multiply with 0, multiply with k, divided by 2, and with k. And if I write this out, this gives us simply 1 over square root of 2. And it shouldn't come as a surprise that we get this. So what we have done in this Fourier transformation is that we now have made a superposition. So the new state is a transformation. So previously we had the computational basis states, which on the block sphere point up and down, but now we are making a transformation. And this transformation now gives us a superposition of the two computational basis states. And if we now take the one state, the transformation of that one, that is again 1 over square root of 2. And now I'm just writing this out directly. So 2 pi of I of 0 times 1 multiplied with 0 plus, and then I have my E, and then I'm just getting pi of I multiplied with 1. And that comes out as 1 over square root of 2, and then I have 0 and minus 1. So what I see now is that the new state, if we call that for y in this specific case, is given by this transformation multiplied with the previous state x, and where u is actually the old traditional Hadamard gate, which is 1 over square root of 2, 1, 1, 1, minus 1. So what we have done with 1 qubit is actually just a Hadamard transformation. So just keep that in mind, because when we get to 2 qubits, 3 qubits, and so on, what you will see is that there is a Hadamard transformation, which we perform on the first qubit, and then there will be, as you will see, a series of rotations on the other qubits. And this is something which we then can express in terms of circuits, or if we just want to look at a matrix times a vector, the quantum Fourier transform is actually going to be defined by the same matrix, which we have here, because the W's are the same. The mathematical expression is the same. So we could actually rewrite everything in terms of this operation, but that is more time consuming. So we are going to break this down in a series of Hadamard operations and rotations, as you will see very quickly now. So let's look at the case with 2 qubits, since we did 1. So let's take 2. So we take the n equals 2 qubit states. So that means that we have n equals 2 to the power of 2, which is equal to 4. So we have the 4 basis states. And when we now look at the typical transformation which we can make, we discussed before the break the type of states which we have for 2 qubits. So the computational basis states which we have are these 4 states which you see here. And these computational basis states are states which I now can represent with this more compact notation. So when I'm running the sum now for the Fourier transform, so my Fourier transform is now simply, did I write it down? Yeah, we wrote it down here. This is going to be the Fourier transform. So I want to see now how a specific state transforms into the new basis. So what happens, for instance, with this 0,0 state? How does that transform when I now perform a Fourier transform on that one? But let's take a small look at these states. So if you now look at the encoding which we can think of, so we are now going to look at the possible encoding. So if we look at 0,0, this is something which we have labeled as state 0. Okay? I have 2 qubits. And if I think of this in terms of a binary representation, this will be 2 to the power of 1. And I have qubit 0. So this is the specific state I'm looking at. So you have a 0 here, which is this one. Okay? and then I have plus, and then I have 2 to the power of 0, and then I also have 0. So let's make arrows here. So this points to that one, and this one points to that one. And if you sum this up, this is equal to 0. That is state 0, okay? So this is just a way by which we are going to encode the information. So qubit, the first qubit is in state 0. The second qubit is in state 0. And then I simply use a binary integer representation. Later, we're going to translate that one into a binary float representation. That's the more compact way, which is often used in the literature. But you see, is this okay? So if we go to the next state, if we look at 0, 1, this is a state which we wanted to label as state 1. And now, if we use the same recipe, so what we have is 2 to the power of 1, and this is obviously multiplied with 0, plus 2 to the power of 0. Let me just take this away here. This is 2 to the power of 1, and 2 to the power of 0, multiplied with 1, and that gives us 1. So this gives us back state 1. And then it's pretty easy to see that 1, 0, which we label as state 2, is 2 to the power of 1, multiplied with 1, plus 2 to the power of 0, multiplied with 0, and that's obviously equal to 2. And finally, just to convince you that we get 3 here, this is the same as 2 to the power of 1, multiplied with 1, plus 2 to the power of 0, multiplied with 1. I actually put the parentheses the wrong way here. I want to have it like this, 2 to the power of 0 times 1, and that's equal to 3. So which are the ways by which we recover these specific states? You can do the same with 3 qubits. Let me give you an example here with 3 qubits. So if we take n equals 3 qubits, what we have then would be a total of 8 states. That's 2 to the power of 3. So we could now say that we have a specific state y, which is given by this state 4. Let's say that. This is the same as a state which is 1, 0, 0, 0. And this state is nothing but 1, 0, no, sorry, not 1, 0, but 0, 1. Tensor product with 1, 0, and tensor product with 1, 0. So if we want to label this as state number 4, so state 0 is qubit 0, 0, 0. This is now equal, if we now use this kind of counting, what we would get is 2 to the power of 2, because now we have 3 qubits, multiplied with 1, plus 2 to the power of 1, multiplied with 0, plus 2 to the power of 0, multiplied with 0, and that's equal to 4, which gives us this specific number. So this is just a way by which we are going to order the different states. And then we are going to rewrite the Fourier transformations in a more compact way. So if we then look at a specific state, so we have our transformed basis, it's going to look like this. So we have a basis, which I'm just going to call for a j here. And that is given by 1 over square root of n. And then I have my sum over y equals 0 up to n minus 1. And then I have a e to the 2 pi of I of j multiplied with y divided by n, and then I have y here. And this y contains now a set of basis states, which I label as 0, 1, up to some n. This is actually something which refers to the type of qubits which I have, up to n minus 1. And these states could then, sorry, this should be n minus 1 here. So what I would have then is now a set of states here, which are going to give me, if I look at this formula, which I put up here, I'm going to have a set of states, which I'm just going to call y0, y1, up to yn minus 1. And that means that this specific state y, this specific number which I want, is given by 2 to the power of n minus 1 times y0, plus 2 of n minus 2 of y1. And this goes all the way down to 2 to the power of 1 of y of n minus 2, plus 2 to the power of 0 of y of n minus 1. Okay? So this is a kind of compact notation, and you see now that this y which you have here, this one, is now going to refer to one of these numbers, 0, 1, up to n minus 1. If you go back to the case we had here, this uppercase n is given by this number. And then we have the qubit, the first qubit, the second qubit. With a 3-qubit case, you have the first qubit, the second, and the third. And these are labeled here. So instead of writing this out in terms of all the qubits, we just write it out in terms of that information. Okay? So that's just the recipe. And that means that I can rewrite the state which I had, the state J, which you saw here. So the state J is something I can rewrite now in terms of n. And now I'm simply summing from y0, 0 to 1. y1 equals 0 to 1. And this goes up to the final one. And then I have yn minus 1 to 1. This is multiplied with, and then I have e of 2 pi of I multiplied with j divided by n. And now I'm summing over all this k equal 0 to n minus 1. And then I have my yk and 2 of n minus k. And this is then multiplied with the state y of k. So the only thing I did now was simply to start using this compact notation. And I can actually rewrite this, and I leave that as a small exercise to you. You can rewrite this as a set of tensor products of k equals 0 up to n minus 1. And then I'm having all this specific state, 0 plus e to the power of 2 pi I times j divided by n. And this is multiplied with 2 to the power of minus k. No, sorry, not that one. I was a little bit too rushed here. I was rushing a little bit. So this should be equal to I of 2 pi multiplied with j of 2 minus k and multiplied with the state 1. So if we now look at one of these specific states, so this is a tensor product of all the specific 1-qubit states. So this expression, if you now look at what you have, So note, so we have that 0 plus this e of 2 pi times j of 2 minus k multiplied by 1. This is something which we can now rewrite. If you just remember now that the 0 is equal to 1, 0. So this is a state now, which is a linear combination. And we also have a rotation in front of it. So we have 0 and 1 is 1 here. So what we can rewrite this one is as 1 of e of I of 2 pi of j divided by 2k. So that means that the transformation which we get, so this state j, the way this transforms into square root of n, and then I have the tensor product of all these guys here, of e of I of 2 pi times j divided by 2, that's the first one, because then we are, sorry, this is just 2 to the power of 0, tensor product with, so can I switch page? Is that okay with everybody? I can just wait a little bit here. Okay, so that's a tensor product with 1 of e of I of 2 pi of j divided by 2. And then this just goes on till the final one, which is 1 of e of I of 2 pi of j divided by 2 of n minus 1. Every operation here is something which we now can rewrite in terms of different gates and different types of operations. So if you now look at some examples, so let's do that. Suppose now that we have the n equal 2 qubit case, and we want to see what happens with the 0, 0 state. So the 0, 0 state, if we do the transformation of that one, that is transformed into 1 over square root of 4, which is 1 over 2. And then I have, because now I'm putting in a 0 here, so this has, in this term, I have 0 here and 0 here, so that just gives me 1. So what I have then is just 1, 1. Tensor product of 1, 1. And if I write this out, this is nothing but 1 over 2 of 1, 1, 1, 1. And this is now a linear combination of the computational basis states. So what I get is that this is 1, 2, and then I get 0, 0, plus 0, 1, plus 1, 0, plus 1, 1. So what I've done with the Fourier transform now is that a state is being transformed into a linear combination of the computational basis states. Now, one of the reasons why this is interesting is that actually this is important when we are going to estimate the eigenvalues of a system, because then we are getting linear combinations of basis states. Because you know that when you have an interaction, the eigenvalue is not equal to the eigenvalues which you would get from the computational basis states. Then it's normally a linear combination. So producing this kind of linear combination through a Fourier transform is something which is going to allow us to estimate the ground state of the system. And you will see next week with the phase estimation algorithm how we can extract the ground state. So as another example, if we now take n equal to 3, and again, I look at the state, or I could look at a different state just to make it a little bit different. So I could now take 0, 0, 1 and see how that transforms. So this is a state which I'm looking at now. And this has 1 over square root of 8. It's going to be given by 1, 1. There's a tensor product of 1 of e of I of 2 pi divided by 2. And it's multiplied by, and then we have a final one here, which is then given by 1 of e of I of 2 pi divided by 4. And when I put everything together, this is going to be 1 over square root of 8, tensor product of 1, 1, with 1 minus 1, and finally tensor product of 1 and I. And when I do the calculations here, this is going to give me 1 over square root of 8. And I'm going to have 8 elements, obviously, because these are 3 qubits. So I have 1 and I, minus 1, and minus I, 1, and I, minus 1, and minus I. And this is something which we can write out as a linear combination of all the computational basis states, which we have again. So we would have 1 over square root of 8, and then we have 0, 0, plus, well, actually it's a minus. And then we have 0, 1, 0, plus 1, 0, 0, minus 1, 1, 0. And then I have the imaginary part, plus I. And then I get 0, 0, 1, minus 0, 1, 1, plus 1, 0, 1, minus 1, 1, 1, parenthesis end, and final parenthesis end. So again, you see that what I've done is to make a linear combination of all these states, and then I look at the transformation of this specific state here. So these kind of manipulations are the kind of things you get when you set up a Fourier transform. Now, one of the things, if we now go back to this 2-qubit case, it's actually interesting to look at the general 2-qubit quantum Fourier transform. So if we just want to write this as a plain matrix vector transformation, so as for n equal to 2 here, the QFT matrix transformation takes a simple form here. And now the only thing which I'm doing is actually to go back to what we discussed before the break, where I put up the general transformation matrix. So if we go back, slowly go back here, this is the matrix which I'm going to set in now for just 2 qubits. So let's take a look at what that one looks like for 2 qubits. This is going to be a 4x4 matrix. So what we get in that case is the following. So let's just do that. So this matrix is now going to be given by, so I'm just going to, so we would have a vector x, which is given by this QFT. And now I have a n equal 2 acting on a vector y. So this matrix here is simply going to be given by 1/2. And now simply putting in the values. So I have 1, 1, 1, and 1. And I have 1, 1, 1. And then I'm going to get I minus 1, minus I, minus 1, 1, and minus 1. And then I get minus I, minus 1, and plus I. And this is simply to do with the powers of e to the 2 pi of I divided by the number of qubits which we have, or the number of states. And you see now that if I start with a state, if 0, 0 is the one I start with, then you know that what we get is this matrix QFT multiplied with the transformations, so I'm just looking at that transformation. So that would be the same as this matrix, which you see here, this QFT of n equal 2 being multiplied with 1, 0, 0, 0. And if you perform that multiplication, this is the same as 1 over 2, and I'm left with 1, 1, 1, 1, which is the case which I had before. So you see the transformation of the 0, 0 state now gives you a linear combination of all the computational basis states. So this state which you have here, this one, is actually the same which we got when we looked at the 2 qubit case here, by just writing out explicitly the tensor products of the different 1 qubit states which we have here. So you see this state here, this is the same as when we operate with this matrix here on that state 0, 0. So that gives us a transformation which we got when we looked at the tensor products. So the tensor product is just us rewriting everything in terms of, if we now look back here, so what we did was simply to take these expressions here and rewrite them in a more compact way. So you should in principle just get the same, obviously. So this is just a kind of sanity check that we're actually getting the right results. So in general, if we do a QFT, so in general, what we have we will have a QFT matrix of n equal to 2 to the power of n, which is actually equal to the following. So we have 1, 1, 1, all ones here, 1, and then we would have an omega, and then an omega squared, up to an omega of n minus 1. Here we get an omega of 2n minus 1. And finally down here we have omega of n minus 1 squared. And here we would get omega squared. Here we have omega to the power of 4. And down here we have omega to the power of n. This should actually be n minus 1 here. This is the uppercase letter n. And this omega is equal to e of 2 pi of I divided by n. So this is a transformation which we are obtaining if we just want to do a matrix times a vector calculation. But this is not very efficient when we want to translate this one into quantum computing algorithms. So what we are going to do now is to rewrite slightly and prepare everything for writing a quantum circuit. So if we look at that specific state which we have, what we are going to use now is a slightly modified description of a state. So suppose now that we take a general state, which I call for state y, and that contains this y0, y1, up to y of n minus 1. So for the 2 qubit state, this could be 0, 0. For the 3 qubit states, it could be 1, 0, 0, etc. So this is the same notation which we had a little bit earlier. And what we had then is that this state here is something which then transforms in terms of, so this transforms in terms of, let me just remind you of the equation here, of 1 divided by the square root of 2 to the power of n. And then we have all these tensor products. So what we would get then would be something like a 0 plus an e of 2 pi of I, and then I have this j value, no, sorry, y here, divided by 2 to the power of 0, multiplied with 1, tensor product with, I'm a little bit fed up of writing all these tensor products, I have to confess that. And this goes on all the way here. So it's now pretty common to actually rewrite. So what we did was actually to write this y in terms of y0 of 2 to the n minus 1 plus a y1 of 2 of n minus 2 plus, and then we have the ny of n minus 1 to a 0. And it's common to replace that one. So this is a binary integer representation. So with a binary float, and that's more common actually, and you will see that in many textbooks. Then what will you have a binary float? Sorry. You would simply represent, if you have a state, you would just write a state like this. If you have a y of k plus 1 up to some y of n minus 1, that will be written as a y of k multiplied with 2 to the minus 1. So this is this corresponding representation you have for float in a binary representation. And then I have 2 to the power of minus n minus k. So this would be a general state. And that means that you would have a transformation of the type. So this state, y, which is given by these different qubits, y0, y1, up to yn minus 1, you can then show that you can rewrite this in terms of, actually I should write like this transforms in terms of 2 to the power of n, and then I have 0 plus e of I of 2 pi of 0, and then I have y of n minus 1 multiplied with 1. And this has then the tensor product with the next one, which is 0 plus e of I of 2 pi of 0, and then I have y of n minus 2 and yn minus 1 with 1. And this just goes on till the final one, which is 0 plus e of I of 2 pi, and then I have 0, and then I have y, 0, y1, all the way up to yn minus 1, multiplied with 1, and like that. So when you now look at 2 qubits, let's do that. And this is where we will stop today, because what you will see now is that typically when this acts on the first qubit, this can be rewritten in terms of a Hadamard gate and a rotation gate. So next week, we are going to express these kind of transformations in terms of gates. So if we go back to the n equal 2 case, what we have then is 0 of y1, which is just y1 divided by 2. And then I have 0 of y0 and y1. This is the same as y0 divided by 2 plus y1 divided by 4. So that means that this state, which I've labeled y, which is now a 2 qubit state, y0 and y1, this is simply given by 1 over square root of 2, and then I have 0 plus e of 2 pi of I, of 0 and y1 multiplied with 1, and then tensor product with 1 of 0 plus e of 2 pi of I of 0 and y0 and y1 multiplied with 1. And when I write this out, this is simply going to be equal to, if I now take as an example, so let me just take that one away. So if my y0, this should actually not be that, this transforms like that. So if I now look at 0, 0, if I plug that in, that is now going to give me 1 divided by 2, and then I have my 0 plus 1 tensor product with 0 plus 1, which is the same as 1/2 of 1, 1 tensor product with 1, 1, which is the same as this 1 of 1, 1, 1, 1. So next week, what we are going to see now is that we can rewrite these operations on the different qubits in terms of Hadamard gates and rotation gates. So as an exercise for next week, try to look at this with 3 qubits and look at how the specific states transform. And then next week, we are going to set up the gates or the circuits for 2 qubits and 3 qubits. And then we can generalize this one, and then we can have a general Fourier transform, a quantum Fourier transform. And when we have that, we are going to look at how we can use this quantum Fourier transform to find the eigenvalues of a quantum mechanical system like the one we have for the Lipkin model. And that would be one of the possible variants for project number 2. And then we're also going to look at how we can implement this with either Qiskit or just write our own code for it. And finally, we are going to use this quantum Fourier transform to study an algorithm which is called Shor's algorithm, which is very important for factorizing large integer numbers. So I know this is not the most exciting state, things which we're going through. I've never been very fond of all this kind of index gymnastics and rewriting of things. But hopefully next week, when we are going to break this down into circuits and gate operations, you will see why this type of representation is more useful than just performing a matrix times a vector calculation. Actually, the fast Fourier transform, this is very much the kind of foundation for that, does not take the discrete Fourier transform in terms of a matrix times a vector. A matrix times a vector, if I take the discrete Fourier transform, a matrix times a vector requires n squared floating point operations. So this is a straightforward, so if I think of the discrete Fourier transform, I actually have, for the DFT or the QFT, that doesn't matter. What we have is a new state, which is given by a matrix, where we know what the matrix looks like, times a previous one. So this matrix is normally a matrix which would be a real or complex, so I'm just writing either complex or real, of dimensionality n times n. So to perform that operation, that requires n squared floating point operations. So the fast Fourier transform, on the other hand, that gives us something which goes like n of log n. So you could think, let me do this in a brute force way and just do the matrix vector multiplication. We could perform the quantum Fourier transform in the same way, just do it like that, as I showed here. So if I use this matrix here, which is a 2-qubit case, I can then rewrite everything and obtain the same result as I did when I rewrote everything in terms of tensor products. The advantage of doing this in terms of these tensor products is that actually saves CPU cycles. So I haven't showed you that the fast Fourier transform goes like this in terms of number of floating point operations, but this is something you can find in every textbook or on fast Fourier transforms and Fourier transforms. So I'm not going to show that here, but we're just going to take that as a well documented result from the scientific literature. And the fast Fourier transform, as I said, if you can really reduce the number of operations from n cubed, n squared, down to n times log n, that is a very important reduction in the number of floating point operations. So next week, we're going to implement the quantum Fourier transforms and use that one to extract the eigenvalues for, let's say, the Lipkin model. So the Lipkin model is going to torment you for the rest of the semester. And somebody here has actually seen that in a course of many body physics. So they're going to have nightmares about the Lipkin model. Okay, guys. See you next time.